Hi everyone. Let's talk about indefinite integrals. In the first exercise, we must find both the derivatives and the most general antiderivatives of the following functions. If you don't know what an antiderivative is, you should watch my previous video. You can find a link to that video in the video description. Let me start with derivatives. The derivative of cosine of x is negative sine of x. The derivative of x squared is 2x. The derivative of 1 over x is negative 1 over x squared. Let's now find the most general antiderivatives. I always ask myself, the derivative of what function will give me cosine of x? And I believe that is sine of x plus c, because I need the most general antiderivative. In the previous video, we discovered that the most general antiderivative of x squared is x to the third power over 3 plus c. And we also discovered that the most general antiderivative of 1 over x on any interval is ln absolute value of x plus c. Note that the operation of taking the derivative is denoted by d dx. You could write that the derivative of x squared is 2x. Mathematicians had to come up with a way to denote the process of taking the antiderivative, the most general antiderivative. And they came up with the following. They used the following symbol they called the integral symbol. The symbol looks like an elongated S. They write that symbol, then they will write a function on the right side of that symbol, and then they will end it with saying dx. For example, if I wanted to say, let's take the most general antiderivative of x squared, I would write integral of x squared, and I would end it with dx. The answer to this is x to the third power over 3 plus c. Every time you see an expression that looks like this, think, find the most general antiderivative of the function x squared with respect to x. That function is written in terms of x. This is the definition of indefinite integral. An indefinite integral of a function f of x, which we denote by this symbol, is simply the most general antiderivative of the small f of x. Said differently, this indefinite integral equals any antiderivative of small f of x plus c, where c is an arbitrary constant. Let's see if we understand this definition by finding some most general antiderivatives, evaluating the following indefinite integrals. If you would like to try this on your own first, stop the video now. I also want to mention that this notation may seem strange and weird, but we will understand why the most general antiderivative of a function e to the power of x is denoted this way in one of the future videos. The most general antiderivative of e to the power of x is e to the power of x plus c, which means that if I want to evaluate this indefinite integral, I get e to the power of x plus c. Evaluating this indefinite integral gives me the most general antiderivative of sine of x. Which function, when I take its derivative, gives me sine? Well, I believe it is negative cosine of x plus c. When it comes to cosine of x, I'm pretty sure I get sine of x plus c, because the derivative of sine of x plus c is cosine of x. Antiderivative of secant squared is tangent of x plus c to get the most general antiderivative. When it comes to secant tangent, I get secant of x plus c. And that is because the derivative of secant is secant tangent. The derivative of which function gives me this expression? I believe the derivative of arctan gives me that function. The next example, the indefinite integral of this expression is arcsine of x plus c. And finally, I get arccosine plus c. Remember, another name for arccosine is inverse cosine, inverse sine for arcsine, and inverse tangent for arctangent. In the previous video, we found the most general antiderivatives for functions of the form x to the power of p and 1 over x. And we realized that the power rule for indefinite integrals, or we called it back then power rule for antiderivatives, was x to the power p plus 1 divided by p plus 1 plus c. And we said that this rule can be used anytime besides p equal to -1, because when p equals -1, this formula makes no sense. You cannot divide by 0. When p is -1, this expression turns into x to the power -1, which is the same thing as 1 over x. And in that case, we realized that the antiderivative, the most general antiderivative on any interval, is ln of absolute value of x plus c. Let's see if you understand how to evaluate indefinite integrals by trying to evaluate these two indefinite integrals. If you would like to try this on your own, stop the video now. Just a reminder that you can download these notes using the link in the video description. I believe that an antiderivative of 5x to the third power is 5x to the fourth divided by 4. Because I want the most general antiderivative, I add c to it. You can double check that this is the right answer. When you take the derivative of this expression, you rewrite the 5, and then you take the derivative of this expression, 4 comes down, cancels with the 4 in the denominator, and you get 5x to the third power, which is exactly what you wanted to get. What about here? I will simply take antiderivatives of each expression. Antiderivative of x squared is x to the third power over 3. Antiderivative of x to the third power is x to the fourth power over 4. And I will add c at the end. And I can again verify that my answer is correct. I take the derivative here, 3 comes down, cancels with the 3 in the denominator, and I get x squared. When I do the same thing here, I get x to the third power. When I get the derivative of c, I get 0, which means when I take the derivative of the expression on the right side, I get exactly this term, or this expression, this function. What we just discovered are the constant multiple and sum rules for indefinite integrals. The constant multiple rule says that if you need to compute an indefinite integral of c, where c is a constant, times f of x, you can simply take that constant c outside of the integral and compute the indefinite integral of f of x. This is what we did in the first example. We took 5, we rewrote it, which is equivalent to taking 5 outside of the integral, and then we found an antiderivative of x to the third power, and we added c at the end. The sum rule says that if you have an indefinite integral of a sum of two functions, you can take antiderivatives of each separately and then add c at the end, just like we did in the second example. Let's see if we understand all the rules we introduced today by evaluating the following 3 indefinite integrals. If you would like to try this problem on your own, stop the video now. In the first exercise, I have 3 functions. I will take antiderivatives separately. And in the first term, I will apply the constant multiple rule. I will rewrite the 3 and then take an antiderivative of x squared, which is x to the third power over 3. An antiderivative of sine is negative cosine of x. Antiderivative of 1 over x is ln absolute value of x. I finish everything by adding the constant c. I can simplify this expression. I see that 3 and 3, they divide out. And I get x to the third power minus cosine of x plus ln of absolute value of x plus c. In a second example, I will first rewrite the function inside of the integral so that I can apply the power rule for indefinite integrals. I can rewrite this as an integral of x to the power 1/2 dx. This allows me to apply the power rule for indefinite integrals, and I increase the power by 1, and I divide by that increased power. At the end, I add c. Let me simplify this. Dividing by 3 over 2 is the same thing as multiplying by 2 over 3, and I get 2 over 3 times x to the power 3/2 plus c. In the last example, before I find the value of the indefinite integral, let me first rewrite the function inside. I don't know a rule for taking antiderivatives of functions divided by functions. Let me first simplify this by writing this expression as the sum of two fractions. When I do that, I get an indefinite integral of x squared divided by x plus 3x divided by x dx. Simplifying these two fractions gives me, in the first term I get simply x, as the second term I get simply 3. Now I can take antiderivatives of each term. An antiderivative of x is x squared divided by 2, an antiderivative of 3 is 3x. I finish my computation with adding plus c at the end.